बिस्मिल्लाहिर्रहमानिर्रहीम रब्बिश शरह सदरी व यस्सिर ली अमरी वाहलुल उक़दतम मिन लिसानी यफ़क़हू क़ौली। अस्सलाम वालेकुम। Today we will continue section 2.5 acceleration, example 2.6 average and instantaneous acceleration from the book Physics for Scientists and Engineers with Modern Physics by Serway and Jewett, 10th edition. The velocity of the particle moving along the x-axis varies according to the expression Vx is equal to 40 minus 5t square, where Vx is in meter per second and t is in seconds. Part A, find the average acceleration in the time interval t is equal to 0 to t is equal to 2 seconds. Solution: conceptualize. Think about what the particle is doing from the mathematical representation. Is it moving at t is equal to 0? In which direction? Does it speed up or slow down? Figure 2.9 is a Vxt graph that was created from the velocity versus time expression given in the problem statement. Because the slope of the entire Vxt curve is negative, we expect the acceleration to be negative. Figure 2.9, example 2.6, the velocity time graph for the particle moving along the x-axis according to the expression Vx is equal to 40 minus 5t square. Categorize. The solution to this problem does not require either of the analysis model we have developed so far and can be solved with simple mathematics. Therefore, we categorize the problem as a substitution problem. Find the velocities at ti is equal to ta is equal to 0 and tf is equal to tb is equal to 2 seconds by substituting these values of t into the expression for the velocity. We know the expression of velocity Vx is equal to 40 minus 5t square. We know that ta is equal to 0 second. Therefore, Vxa is equal to 40 minus 5ta square is equal to 40 minus 50 square is equal to 40 meter per second. We know that tb is equal to 2 seconds. Therefore, Vxb is equal to 40 minus 5tb square, which is equal to 40 minus 2 square, giving us the answer of Vxb equal to plus 20 meter per second. Use equation 2.9 to find the average acceleration in the specified time interval delta t is equal to tb minus ta is equal to 2 seconds. Ax average is equal to Vxf minus Vxi divided by Tf minus Ti. We know that Vxf is equal to Vxb, Vxi is equal to Vxa, Tf is equal to Tb, Ti is equal to Ta. Therefore, Ax average is equal to Vxb minus Vxa divided by Tb minus Ta. We know that Vxb is equal to 20 meter per second, Vxa is equal to 40 meter per second, Tb is equal to 2 seconds and Ta is equal to 0. Therefore, Ax average is equal to 20 meter per second minus 40 meter per second divided by 2 second minus 0 second, giving us the Ax average of minus 10 meter per second square. The negative sign is consistent with our expectation. The average acceleration represented by the slope of the blue line joining the initial and the final points on the velocity time graph is negative. If we study the graph, we see that at Ta is equal to 0 second, Vxa is equal to 40 meter per second, at Tb is equal to 2 second, Vxb is equal to 20 meter per second. If we calculate the slope of the graph, it comes out to be negative, therefore the acceleration is negative. Part B. Determine the acceleration at t is equal to 2 seconds. Solution. Knowing the initial velocity at any time is Vxi is equal to 40 minus 5t square. Find the velocity at any later time t plus delta t. Vxf is equal to 40 minus 5 bracket t plus delta t whole square. This is equal to, if we use the formula of a plus b whole square is equal to a square plus 2ab plus b square. If we use this formula, we get 40 is equal to minus 5t square minus 10t delta t minus 5 delta t square. If we look at TF is equal to t plus delta t, then VXF is equal to 40 minus 5 bracket t plus delta t whole square. We know the formula, bracket a plus b whole square is equal to a square plus 2ab plus b square. Therefore, bracket t plus delta t whole square is equal to t square plus 2t delta t plus delta t whole square. This gives us VXF is equal to 40 minus 5 bracket t square plus 2t delta t plus delta t whole square. If we open the bracket, we get VXF is equal to 40 minus 5 t square minus 10t delta t minus 5 delta t square. Find the change in velocity over the time interval delta t. Delta Vx is equal to Vxf minus Vxi is equal to minus 10t delta t minus 5 bracket delta t square. Delta Vx is equal to Vxf minus Vxi, which is equal to 40 minus 5t square minus 10t delta t minus 5 bracket delta t square minus 40 plus 5t square. The value of 40 and 5t square cancels. Therefore, delta Vx is equal to minus 10t delta t minus 5 bracket delta t square. To find acceleration at any time, divide this expression by delta t and take the limit of the result as delta t approaches 0. Ax is equal to limit delta t approaches 0 delta Vx over delta t. This is equal to limit delta t approaches 0 minus 10t minus 5 delta t. Since delta t approaches 0, Ax is equal to minus 10t. Ax is equal to limit delta t approaches 0 delta Vx over delta t. We know that delta Vx is equal to minus 10t delta t minus 5 bracket delta t square. Therefore, Ax is equal to limit delta t approaches 0 minus 10t delta t minus 5 bracket delta t square divided by delta t. This makes Ax equal to limit delta t approaches 0 minus 10t minus 5 delta t. Since delta t approaches 0, we obtain that Ax is equal to minus 10t. At t is equal to 2 second, Ax is equal to minus 10 bracket 2, giving us Ax equal to minus 20 meter per second square. Substitute t is equal to 2 second, Ax is equal to minus 10 times 2 meter per second square, which is equal to minus 20 meter per second square. Because the velocity of the particle is positive and the acceleration is negative at this instant, the particle is slowing down. Finalize. Notice that the answer to part A and B are different. The average acceleration in part A is a slope of blue line in figure 2.9 connecting points A and B. The instantaneous acceleration in part B is the slope of green line tangent to the curve at point B. Notice also that acceleration is not constant in this example. Situations involving constant acceleration are treated in section 2.7. So far, we have evaluated derivatives of a function by starting with the definition of the function and then taking the limit of a specific ratio. If you are familiar with calculus, you should be able to recognize that there are specific rules for taking derivatives. These rules, which are listed in Appendix P6, enable us to evaluate derivatives quickly. For instance, one rule tells us that the derivative of any constant is 0. As another example, suppose x is proportional to some power of t, such as in the expression x is equal to a(t(n), where a and n are constant. This expression is a very common functional form. The derivative of x with respect to t is dx over dt is equal to n a t(n minus 1). Applying these rules in example 2.6, in which Vx is equal to 40 minus 5t square, we quickly find that the acceleration Ax is equal to dvx over dt is equal to minus 10t, as we found in part B of the example. In this problem, we are given with the function Vx is equal to 40 minus 5t square. To find the acceleration, we'll take the derivative of velocity with respect to time. We know that the 40 is a constant, therefore the derivative of 40 is equal to 0. The derivative of minus 5t square is equal to minus 5 times 2 multiplied by t, giving us the acceleration in the x direction as minus 10t. May Allah bless us all. Thank you for watching. Allah Hafiz.